What's up, everybody? My name is Jason Dobies, and today I'm here to talk to you about operators. Before we get started, a little admin type stuff. The way I understand this is you're going to be viewing this recording in a chat. I'm going to be there alongside of you. So I invite all of you to speak up in chat, ask questions as we go. I'm going to post some links to make things a little bit easier to follow. A lot of the code that I showed today, a lot of the examples are all available in GitHub. So I'll make sure that I paste that in chat for you if you want to follow along, if you want to run through the examples on your own afterward. But like I said, feel free to participate as things are going. One of the benefits of it being recorded is I don't have to constantly look over and see if there's something going on in chat. So be vocal, ask questions, and let's have a little bit of fun with this. So before we get into it, just like I said, my name is Jason Dobies. I'm a developer advocate at Red Hat, focusing primarily on our OpenShift product. OpenShift is our enterprise version of Kubernetes. Assuming if you're in this talk, you at very least know what Kubernetes is. OpenShift is built on top of Kubernetes. So we did the normal Red Hat thing of hardening it, making it enterprise and production ready. We layer on a ton of extra developer utilities, a UI, and provide an entire suite of certified software that we've shown that, yes, this worked properly with OpenShift and things are going to continue to function. We'll see a little bit of OpenShift today. We'll see a little bit of Minikube today. So we're going to bounce around to a few things. I'm the author of the O'Reilly book, Kubernetes Operators, came out earlier this year. You can see that QR code is going to point you to my Twitter account. I have a slide with that information later on for how you can contact me. Before we get into talking about how to write an operator, I think it makes sense to see a quick example of what they're capable of. Seeing the different pieces is going to help you map the concepts to a real tangible example, and it's going to give us something to refer to as we go through the concepts in the slides later. So I have the Red Hat AMQ Streams operator already installed, and when I click in through it, you can see the different resource types that are available to us. Also known as provided APIs. This is going to be ours, the end user's way of interacting with the operator. So in this case, we're going to elect to create a Kafka broker. And you can see here we have a graphical view on top of the different configuration, the number of brokers we want, the number of zookeepers, and so on. If you come from a Kubernetes background, you'll be more comfortable looking at the YAML view, but all of the configuration is available. And you'll notice that the kind is Kafka. Now that part's going to look a little bit strange to you if you have a Kubernetes background because you're probably thinking that's not a valid kind. We're going to talk about that in a little bit when we get to the concepts. But keep in mind that was our API into interacting with the operator. Now we can see it's created a number of child resources as a result of that. My single Kafka resource has produced some secrets, some services, and a number of running pods. And you can see here the first thing that comes up is this zookeeper cluster. So we have our 3 zookeeper pods created. Only once they're running do we have the actual Kafka broker itself stood up. The operator has this intelligence and understands that we can't do anything until the zookeeper cluster is running, and only then can we actually get into the pods itself. So what I'm going to do is I'm going to select one of these pods, and I'm just going to run a basic command to show us all of the topics that are currently deployed inside this cluster. No surprise, there's not going to be any because we just created the cluster. Well, let's go back to our operator. You'll notice that under provided APIs, we also have one for a Kafka topic. And again, if we look at the YAML view, this is a Kubernetes resource of type Kafka topic. And I'm going to create it. And in a couple seconds, it shouldn't take long, it's going to tell us the topic's been created. Now, there's no underlying Kubernetes resources for this. There's no pods, there's no deployments. The operator didn't have to do anything with Kubernetes itself. It knew to reach out to the cluster to make the appropriate calls to create the topic, and we can see now that the topic's available to the cluster. So the important takeaway there is these APIs don't necessarily have to create Kubernetes resources. The first one did. The Kafka broker itself deployed an absolute ton of different Kubernetes-based resources to get things running. But the Kafka topic resource is pretty cool because the operator can expose it as an interface, and the users will go through Kubernetes like normal to interact with it, but it understands that instead of creating a resource, it's going to reach out to the broker and set some configuration. With the demo out of the way, let's go back and talk some basic concepts about operators, kind of what brings us here, what they're trying to solve, and then that way we're going to go from there and dig into actually writing one. So why are we talking about operators? Why are you here in this talk? It's particularly interesting because at this point, they've definitely become a buzzword, but at the same time, I'm not sure how much the audience for this type of talk is really going to understand what they are just yet. So let's start at the beginning. Why are we doing this? What is it we're trying to solve? And if you've ever done anything with Kubernetes, you know, deploying a simple application is pretty easy. You take your application, you package it inside of a OCI compliant image. Most people will consider this a Docker image. And then you deploy it inside of your cluster. And then we have a running container, or in Kubernetes terminology, a pod, if you're not familiar with it. And that's simple. The problem is most applications are not actually simple. Deploying complex applications, I entertained calling this deploying real applications, because anything beyond hello world that we're going to use to money off of is complicated. There's a lot of pieces to it. So instead of just a single image, we're typically dealing with multiple images, especially if we've adopted a microservices architecture where we really split our application out into these smaller, fine-grained pieces of functionality that we can update independently and so forth. So we have a number of images. And once these images get deployed as containers, they have relationships. They have some shared configuration. They have individual configuration. They have networking between them that says this service can talk to these other services, but this one should be left alone. We have vaults in play to keep our secrets. We have databases. We have a variety of different storage mechanisms. In other words, there's a lot of moving parts when you move past your hello world, simple one container, one image application. And again, all of that is just getting the application running in the first place. How do you keep it running? All of the tasks that go into taking your application and making sure it functions beyond your initial smoke test. That includes upgrades, where you may have some images in your entire architecture getting upgraded, but not everything. You can have pods and containers go down and become inaccessible. You can have new connections need to be established. You can have databases that need to be scaled up, or containers that need to be scaled up. And you can have things just flat out crash on you and your application have to react to it. Now, again, this is all for these more real world, more complex applications, but they're a very real problem that containerized architectures are starting to see. So what is an operator? It's a pod. And depending on how you came to this talk, you may have heard them talked about with almost this black magic type of thing of, oh, do you have your operator that's doing all of this deep insight? And it tends to throw people off initially. Start to think, is this really hacked directly into Kubernetes? Is this some kind of extension, or does it modify Kubernetes in any way? It's simply a pod. So start there with your understanding. More importantly, it's your pod. It contains the logic for your particular application. And again, that logic is going to include everything from basic installation of your application to keeping it running and scaling and maintenance and upgrade. And then it's your API. And if you think back to the Kafka example, we've seen this already, where my operator is telling the user, hey, you can create these resources. Here's the configuration you can put in them. And I, as the operator, are going to take care of everything else. So our Kafka end user doesn't need to know how many pods are created or how many secrets or how many services. It understands that the API is create a Kafka broker, create a Kafka topic. And then that operator goes and talks to Kubernetes for you. It makes all of the necessary calls to create those deployments, create all of the networking configuration, and again, ensure they're running. So anything it needs to do in terms of scaling, it's going to talk directly to the Kubernetes API. So who can write operators? Not going to lie, I know this is a bit of a cop-out answer, but I really wanted that structure on the previous slide. But it is kind of a valid question. You don't have to be a programmer. You don't necessarily have, first of all, you certainly don't have to be a Go programmer, despite the fact that much of Kubernetes is written in Go. There are frameworks out there for writing operators in Java and in Python. Again, since it runs as a pod, if you can get your code running inside of a pod, you can have a functioning operator. Now, there is a project in the CNCF called the Operator Framework, and it's an umbrella for 3 separate projects made to facilitate writing operators, make it a little bit easier, make their management easier. The Operator SDK is what you would expect from an SDK. Got some code generation, it's got some ability to build your operators, to test them, and so forth. Operator Lifecycle Manager, or OLM, is the piece that we saw during the Kafka demo that listed all of our operators for us. Think Yum for operators, where you're able to subscribe to particular channels, and OLM will go ahead and update your operators when new versions come out. It will keep them running and healthy in case anything goes wrong with the running operator itself. And then operator metering, again, what you would expect out of a product named metering. Going to keep some statistics on which operators are being used and the resources they're consuming. Now, I said earlier that you don't have to be a Go developer. The Operator SDK currently supports 3 different, I'm going to say languages is probably the best way of putting it for writing operators. You can, of course, write them in Go like you normally would, directly code into Kubernetes. But if you're an existing Ansible shop, or you already have some infrastructure built on top of Helm, you can use the Operator SDK to package up that existing technology and run it as if it were an operator. And we're going to see that a little bit later during the demo. So where do our operators run? This is the easy answer at this point. They run on Kubernetes. Any version of Kubernetes, because at the end of the day, this uses built-in concepts to Kubernetes. There are no weird extensions. There's nothing specific to OpenShift. This is all functionality that uses the built-in extension points for Kubernetes without at all changing the installation or invalidating it. And of course, since OpenShift is in fact enterprise Kubernetes, your operators will run there as well. And how is going to take a little more than a slide. We're going to spend the next couple of slides talking about the different pieces of Kubernetes that we use for assembling operators, some best practices, and things like that. So let's start with an overview of the variety of steps that's going to take to build an operator. I think it makes sense to lay these out first, and then over the next couple slides after that, we're going to dig into each of these pieces individually. So the first thing you're going to need to do is define your interface into the operator. Again, these are the resources that we saw in the Kafka operator that gave us the Kafka broker, the topics, and so on and so forth. This is how your user is going to interact with your operator. It's usually a good place to start when writing any application, is to think about how the user is going to interact with it. We're then going to find a way to hook into Kubernetes as a controller. And that's going to give us mechanisms where Kubernetes will notify the operator when things have changed with our resources that we need to react to. And then comes the fun part, actually implementing our logic, taking the necessary steps to deploy and manage our application. When you're using something like an SDK for generating and running your project, this should be the meat of where you spend your time. And it should be a pretty easy ramp up into this point where you can sit down and actually start to write code that does what you need. Of course, we're all going to be very good, disciplined programmers, and we're going to test our code before we go through the steps to build the operator and actually deploy it directly inside of our cluster. And again, remember, building means creating an image out of our operator code. Because again, an operator is going to run as a pod. We're going to need an image to do that. So let's dig in. For the interface, you need to understand the concept of custom resource definitions. This is built into Kubernetes. As of Kubernetes 1.16, they came out of beta and they're now a GA level a piece of functionality or feature in Kubernetes. They give us the ability to create our own resource types. So on the left, you'll see the types of things you're typically used to doing with Kubernetes. That API version is effectively a namespacing and versioning construct. So you see there for deployment and service, these are the built-in namespaces that come with any Kubernetes distribution. And these kinds or resource types are the kinds you've worked with elsewhere in Kubernetes. I want a deployment, I want a service, and things like that. I want a config map. We have the ability with custom resource definitions to create our own resource types. So you can see on the right side there that we have our own namespace, we have our own versioning scheme, and then we can name the type or the kind anything we want. And then when users go to create that resource, they're going to use the name we give it. So the next couple slides are going to break down the skeleton of a custom resource definition. It's not completely full, but I've taken out a lot of the boring stuff that isn't really relevant to understanding what goes into them. So at this meta level, the kind of basis for creating them, keep in mind a custom resource definition, or a CRD for short, is in fact another resource inside of Kubernetes. So you'll see that the API version is out of the Kubernetes namespace, and the type itself is just a custom resource definition. And a lot of this stuff is just identifying the resource type that we're creating. So you'll see here, this whole example, both in the slides and then the demo we're going to see after it, is for a fairly simple visitor site application, where when visitors go to the web page, it's going to simply send a call back to a REST API, which is going to store into the database a little bit of information about the client. I believe it's IP address, a timestamp, maybe something else. Anytime you refresh the page, we're going to see a new entry stored into the database, and then the page is just going to show the current state of the database to us. So front end using React in JavaScript, back end using Python, and then our database is going to be MySQL. It took me a second to remember what database we were using. So keep that in mind, that we are looking at a very traditional front-end, back-end database type of application, but it's going to ultimately add up to 3 running pods and then some configuration between the 3 of them that say how to contact the different pieces. So for this, we're choosing to call it our visitors app. And again, this is going to be the resource type that users create to start up and deploy one of these visitors applications. This .example.com here is going to be simply namespacing stuff that we'll see in a little. So the basic structure of a custom resource definition, a lot of this stuff is going to look similar to the structure of any resource inside of Kubernetes. Now, once we dig in a bit, under the spec for the CRD itself, we chain quite a bit down to validation and so forth. The important part here is this spec field. Now, each custom resource is going to have 2 main sets of data. The spec, which is what users enter to describe the desired state of the resource, and then the status, which is set by Kubernetes and, more importantly, our operator, to give some information back to the user on the state and the details of that running resource. Now, again, we're defining the resource type here, the resource definition. So this spec is going to tell us that when users create a visitors type resource, they can specify 2 fields, a size and a title. The size is going to be an integer. The title is going to be a string. Those are going to be used by our operator to configure the running visitors application. Now, I'll tell you what's actually happening is the size refers to the number of backend services. So if we wanted to scale up that REST API, we could change that number at the visitors app level. And the title is simply displayed on the dashboard for the visitors app, primarily as an example purposes. This is going to give us the ability to let the user have a single pane of configuration that they want to configure the visitors app. These are the things that make sense logically. It's our operator's job to pick and choose that size should go to the backend services, backend deployment configuration, and title should go to the front end configuration. And then we can see here, we can indicate that only the size should be required. That's going to give us some validation at the Kubernetes level. So if I try to submit a resource that is missing this size variable, Kubernetes is going to pitch it back to the user and say, hey, you at very least need to specify size. Similarly, if we include other values that are not size or title, Kubernetes is going to pitch that resource back as invalid. So very little that we have to do in the custom resource definition to get that front level validation. I'm going to say superficially, but at the end of the day, it's an open API schema. So anything you can do with that, you'll get for free once you define your custom resource. So that was the resources spec. Again, that's what users are going to specify on the resource itself as the desired state, as what they want out of this resource. The status field is what the operator is going to set on each of those custom resources that the user can later query and see some information about that running resource. Again, we're creating the definition here. So we are telling this type that it is going to have these fields in the status. And in this case, we're going to have two fields, backend image and front-end image. Again, it's more for demo purposes, but the user is going to create a visitors app, and in the status, the operator is going to tell the user, this is the specific Docker Hub image and tag that I'm using for the backend REST API, and this is the specific image I'm using for the front-end API. Maybe not the most useful of information, but it is something that only the operator would know, and this is a chance for it to make it available to you. Like I said, there's some other things going on in the CRD that I'm not going to talk through on here. I don't want this in a 45-minute talk. This can't be completely exhaustive. I'm just trying to highlight the touch points that you're going to care about. So to summarize that, we create our CRD, giving it a name and a namespace that belongs to us as the developer. We're going to create the spec in the CRD that says, when creating a resource of this type, these are the fields that you can specify, and then optionally set some of those as required. And then we're going to define the status, which says these are the fields that you as the end user looking at this resource should expect that the operator is going to keep up to date with the resource's state. Now this itself is an example resource of that particular CRD. So you'll notice our namespacing versioning construct here. I simply shoved it in example.com and called it v1. Remember earlier we saw that the name of the CRD, the name of the resource type, was visitors app. And we defined that it can take two things in the spec, a size and a title. And again, if I had added extra fields here, or if I had omitted size, once we try to create this resource, Kubernetes is going to run that basic validation for us and immediately pitch it back. So that's the interface. How about the controllers themselves? There's a lot going on in this picture, so rather than let your eyes wander over, please just kind of try to follow the red line and things will go a little bit easier to understand. So our end user is creating or modifying a custom resource. Note the word here, desired state. If you're new to Kubernetes, or if you really just haven't necessarily looked into the guts of it, that's all you're doing when you interact with Kubernetes. When you create a resource, you're telling Kubernetes, this is what I want the end result to be. Kubernetes then takes that resource and passes it to any controllers that have what is known as a watch on resources of that type. And those controllers get notified, hey, you need to do something with this resource. That do something is called reconcile, and more generally called the reconcile loop. Now what you'll see in the controller is, don't expect to have these very fine-grained methods that say resource was added, resource was deleted, resource was updated. This reconcile is meant to be run anytime Kubernetes decides we need to check the desired state that the user requested versus the end state or the actual state of reality. So that reconcile's job is to take a look at the user parameters and make sure the external world reality reflects what is desired in the resource. Ignore this bottom loop. We're going to come back to that in a couple of slides. Once it has done that, once it has matched reality, it's going to update the status on the Kubernetes resource just to give, again, some information. Anywhere from monitoring type information to status within the system. You can picture the Kafka example from earlier, returning that you have however many topics or something like that. So whatever information the operator has decided should be specified and should be visible to the user, it'll put in the status, which the next time the user looks at the resource will be updated based on what the operator set. So that was our trip through the controller itself. Most of that plumbing is handled by Kubernetes. The important part to realize is that reconcile is where your business logic is going to lie. Anytime Kubernetes decides you need to double check the reality of a resource versus what the user desired, it's going to call this reconcile loop. And I'm saying it that way because it could be if the resource was initially created or if the resource was updated. Now, when we get to the SDK demo in a bit, you're going to see that the bulk of our work lives inside of this reconcile request. So we're going to look at a little bit of code. Like I said, and I'm hoping that as I follow along in chat, I've at least by now pasted the GitHub repository. But I'll send you the code so you can take a look at what happens in the reconcile loop. It's tedious to look at code in a talk like this. So we're going to see it in the demo. I'm going to pinpoint a few small things. But really what I want to convey is some general ideas and things to take into account during this reconcile loop. And the first is going to be idempotency. We don't, let me put it this way, Kubernetes will call the reconcile loop multiple times. And if you don't write your code correctly, you could result in duplicate resources. So for instance, if you treat your reconcile loop as always being a create request, then the next time Kubernetes calls it, either because a resource has been updated or for whatever other reason, you're going to recreate all of the resources you previously created, and all of a sudden your application is going to spiral out of control. So you need to understand that multiple calls through this reconcile loop should always have the same result at the end of the day. And again, the most obvious point there is the difference between create and update. At first request of the operator when a resource is created versus any other time that the user has changed something or edited a value or not edited a value, and Kubernetes still decides to run through the reconcile again for a number of different reasons. Point being, your code's got to be smart enough to not duplicate things and to check what actually exists, what's desired, and then figure out the delta there and only apply the changes. Now, resource deletion will still go through an operator. That said, Kubernetes is going to take care of deleting the resource inside of Kubernetes itself. So the actual resource that we created with a kind and an API version and some configuration, Kubernetes will delete that for you out of its internal stores. It's your job as the operator. You need to do some kind of external cleanup. If your operator is connecting to a legacy system or some sort of external system that is not creating pods and deployments and services, but is instead making calls out to some sort of external database or some kind of external system, you're going to want to use what's known as a finalizer. Without going too much into the mechanics, just be aware of the term and understand that it gives you the ability to tell Kubernetes, before you delete this resource from your stores, I want you to call the operator and let it do any kind of cleanup it needs to do. Then the operator takes those steps, removes the finalizer, and then pitches it back to Kubernetes so it can do its normal garbage collection of resource. The idea of requeuing a reconcile request is absolutely something we're going to do. We're going to see it a little bit during the demo itself, but it's very possible that your operator is going to want to return this reconcile request and say, hey, do it again. Run through this reconcile request again on my operator within my code. Perhaps wait a couple of seconds and try it again. And we see that in the second point under this impact section, this non-blocking. So let's say let's take the Kafka example. The Zookeeper cluster needed to be running before we can create the brokers. So it's a bad practice for the operator to just sit there and take up Kubernetes resources while it's waiting for these Zookeepers to start up. There's definitely idle time where the images are downloading and the pods themselves are being created, where the operator's not doing anything, just waiting on the pods to start. And only once it detects that the Zookeeper pods have started will it go and continue and install the rest of the pieces. Rather than blocking and having these Kubernetes resources held open, the operator has the ability to return the reconcile and say, cool, I want you to notify me again in 5 seconds or in 10 seconds. And then Kubernetes will take that and requeue the reconcile request. And that way it goes through and it can check if the Zookeepers are up. And if it's not, then it does the same thing. And if it is, it's going to continue down the process of the brokers and again, the other pieces. The point being, we should not block and hold the operator, the reconcile loop open for long periods of time if we can avoid it. Along those lines, keep in mind that we are making calls back into Kubernetes very frequently inside of an operator. We're going to ask for the resource and to get its current state, and we're going to be making calls into Kubernetes to deploy pods and other resources. So we're going to want to be cognizant of the fact that there are other workloads on the cluster itself. We're not going to want to thrash against the Kubernetes API calls. We're not going to want to bombard the system with a ton of resource creation if it makes sense to throttle in, if we have that ability. And at the end of the day, that's up to the operator developers, but it's definitely something to keep in mind that you should be a good citizen to the rest of the cluster and not assume that you're running in a bubble and you can just thrash against Kubernetes itself. Now, I mentioned child resources. Realize that in many cases, your resource, our visitors app resource, is going to create children resources inside of Kubernetes. It's going to create deployments. It's going to create services. There's ways to tell Kubernetes that these new resources we're creating are children of the parent custom resource. That's extremely important to do because that lets Kubernetes garbage collection take care of all of those children. So if I deploy my visitors app and it deploys 3 services and 3 deployments that are all marked as children, when the user deletes the visitors app resource, Kubernetes garbage collection kicks in and takes care of deleting the deployments for us and deleting the services. And what that means is that finalizer I mentioned earlier is typically not necessary. In most cases where my operator is taking a single resource and creating multiple Kubernetes resources, if I create this relationship correctly, garbage collection comes for free, and Kubernetes handles all of that for me. And then naming, just be cognizant of the fact that if you are going to let multiple resources be created in a single namespace, you're going to want to have some randomization in that child resource naming. You can't simply call it database because the next time you deploy a custom resource, it's going to try to create a child resource called database, and that's going to be a clash because now we're looking at 2 deployments in the same namespace with the same name itself. So as for build and deploy, remember that an operator runs as a pod, so it's going to need an image. Now realize there's 2 different images in play. There's the application image itself, and in hindsight, I probably should have put images if you're looking at an application that deploys multiple pieces. Visitors app is going to deploy a front end and a back end component. Each of those have separate images. So this is certainly part before you get to the operator of writing your application itself. The operator is packaged as an image, so we're going to need the operator image. We're going to need a way to deploy that operator image. We saw OLM earlier, but generally speaking, it's simply a pod. So your normal YAML that can take an image and get it running inside of Kubernetes can be used to deploy the operator as well, but you still are going to need to provide that to your users. Now your operator is making calls into the Kubernetes API, it's going to need a service account to authenticate against. So that way your operator calls come from a specific service account or specific authentication. Along those lines, we're going to need a role as well. And we're going to want to be as restrictive as possible with that role. Yes, it's going to be a little bit more open than you may be used to for typical service accounts, but your operator is going to be creating, deleting resources, so those permissions are going to be allowed. But also take some time to review what that role has access to. We'll see in a little bit, the operator SDK grants things pretty permissive by default, so you're going to want to strip out some of those that you don't actually need. And then the last piece just combines the 2. The role binding is what connects our service account to our role. So that way those permissions are valid. Once we get everything in place, our operator can function correctly. So that was a whirlwind tour of a bunch of concepts and best practices. Now let's take a look at actually writing one of these. Let's get to a terminal, let's see some code and see how things actually look. Okay, so what I want to do now is take you through the process of actually writing an operator using the SDK to generate a lot of the project source for us. I have about 10 minutes to do this and there's a lot to see. So come with me on the concepts and I'm going to make the code available so you can go back and take a look at some of the specifics at an easier time when we're not trying to race through a session here. So I'm going to tell the operator SDK to create us a new operator. While it's doing that, I'll point out I'm in my Go path because this is at the end of the day going to be Go code. And if we take a look at the files created, we're going to see it generates a Docker file for us, which is very cool because our operator is going to be deployed and shipped as an image. So having a stubbed Docker file is pretty handy. It's going to generate those other pieces I talked about of the deployment for the operator itself, the service account the operator is going to run as, the roles, and then the binding between the 2. Again, be sure to look inside that role. We don't have a lot of time today, but you will notice the SDK generates it is extremely permissive. So you're going to want to strip down what privileges it grants based on what it is your operator is actually doing. And then the rest of this is the skeleton Go code that we're going to flesh out over the course of this. What we've done so far, we just have the basic project. We're going to run this add API command. And remember that API is pretty synonymous with CRD. So this is going to generate a basic CRD for us, as well as some of the skeleton Go code for the resource created by the CRD. We scope it to our namespace with some versioning information, and then we're simply going to call the resource type the visitors app. Now, if we pull up the CRD for it, there's going to be a lot going on the screen, but you can see a fair amount of this came from the slides, or I should say the slides came from this example. So it generated us metadata about the resource type itself. It generated for us a spec and a status holder. You'll notice that they don't have specific information in it because we haven't told it about that yet. And that's fine. We're going to do that now. So what we're going to edit is this types file. Now, this is a Go-based file that is meant to capture or define the objects we're going to use inside the operator itself. So it generates the spec object, which I'm going to copy and paste in now. These are the two values that I described earlier for what the visitors application does. Just keep in mind what I'm writing here. You're going to see those come up in a minute. I just do them for example purposes. And then we're also going to want to update the status object, remembering that the spec is what the user is going to specify when they create a resource, and the status is used by the operator to convey information back to the user. Now, whenever we edit the types file, we need to run this generation command for some encode stuff. We're also going to run the generate CRDs command. And this one's a lot more interesting. Now, if we go back into our CRD, we look at our spec section, and now we have those properties that we defined inside of the Go code. So our size and our title, we took the description from the comments, or I should say the SDK took the description from the comments. It also populated the status for us with the back end and the front end image. Point being, we can define things purely in the Go code, and we don't have to worry about trying to keep the CRD itself in sync. The SDK will do that for us, and it'll slurp the necessary information out of the types. So right now I could deploy the CRD in a custom resource and nothing would happen. The custom resource would get deployed correctly, but without a controller, Kubernetes doesn't have anyone to notify. So that's our next step. We define our API, which is our CRD, our custom resource definition. Now we're going to add a controller. Scope that controller specifically to the CRD we created, referenced by its API version and kind. And you're going to see it generates for us this controller file. So we're going to edit that in a second. First, I'm going to cheat. So before I do my cheat, notice that we simply have this controller file in here. I'm going to run this command that's going to copy over a number of other files. And this is actually my business logic. There's a fair amount of code in here. I'll make the GitHub repository available to you to look through it. But I do want to comment on a few general concepts that you see in all of these. So for backend, front end, and MySQL, these are going to be the resource definitions for those child resources. So again, our visitors app is going to be consisting of 3 pods with 3 services in front of each of those. Now that definition, and again, there's a lot of stuff going on in here, so bear with me, looks an awful lot like YAML. In fact, let me get to the deployment itself. The Kubernetes library for Go gives us access to all of these objects. We're going to build them up in a very similar way we would build up a resource in YAML. And even at the structure, you can figure out what's going on here, that we have a deployment and a deployment spec, and we're ultimately exposing ports and so on and so forth. So this file, the front end, and the MySQL are all simply creating the resource definitions for all of our child resources. The one line I absolutely want to point out is the set controller reference. This is establishing that parent-child relationship between the visitor's resource and this deployment or this service. And that's going to help the Kubernetes garbage collection. It's going to help us establish our watches. The other piece I want to show you is common. And without going line by line here, realize that this is written in such a way to be idempotent. So it's not create deployment, it's ensure deployment, or make sure the deployment exists. So what's going to happen in this code is we're going to use the pre-authenticated Kubernetes client, and that's given to us by the SDK. And I say pre-authenticated, it's going to be using the service account associated with our operator. And I'm going to use that to query Kubernetes and say, hey, do you have this deployment? And if it does, cool, that's exactly what we wanted. We know we wanted this back-end deployment, this front-end deployment. If it doesn't, we're going to create it. And this is that idempotency that's going to let this reconcile always call ensure deployment without it resulting in multiple things being created. So again, all of this code is going to be available to you to take a look at afterwards and go line by line through. I know I'm kind of speeding through things because there's a lot to establish here. But try to hold on to the bigger concepts at play here, that we're establishing the child resource definitions. We've written some utility code that's going to either create them if they don't exist, or if they do, it's just going to do nothing and not duplicate them. Now inside the controller itself, there's two methods we care about here. One is this add method, and this is going to establish our watches. Now the SDK establishes a watch on our custom resource itself, and that's good, we want that. But we also want to know about any resources owned by the custom resource. In other words, if the visitors app creates a deployment for the backend and a service for the backend, and one of those changes for whatever reason or disappears, we want, as the operator, to be notified. So we need to create watches for services who are owned by our particular resource. Or I should say resources of our particular type. We also want to add it for deployments. So these are all of our watches. There's ultimately 3 of them: visitors app, services belonging to the visitors app, and then deployments belonging to the visitors. If I scroll down a bit, the other method we want to get to is this reconcile method. And this is the reconcile loop. This is the bulk of what our operator is going to be doing. Now, the SDK generates a stub working operator for us that's going to fetch the instance, create some new pods. It's cool that they did that, but ultimately there's very little of that code I care for. I do care about this initial piece that fetches the instance, because when reconcile is called, it's simply told this is the name of the resource that's being requested. We have to, as the operator, go to the Kubernetes API and retrieve that resource information. So we're going to leave that code in there. That's what this block is doing up here. And I'm going to paste in some more cheat code that I'll very quickly talk through because it's not very difficult to follow. We run our ensure methods, these idempotent creation methods that say, I want to deploy MySQL, which is the secret, the deployment, and the service. Then we have a method that checks to see if MySQL is running. It's going to check to see if the pods exist. If they do, it's going to report that it's running. If not, we're going to requeue the reconcile after a small delay of 5 seconds. And this gives us the ability to release the resources back to Kubernetes while that MySQL startup does its thing, the image downloading and so on and so forth. And then we do the same for the backend and the front end. If MySQL is up, we can continue and we can make sure the deployment and the services exist. So with that whirlwind tour through a whole bunch of code, we want to test our operator. Now we could build it into an image and deploy it into the cluster, which is very heavyweight for testing purposes. So the SDK gives us this run command where we can say, I want you to run the operator as if it was in the cluster, but run it locally. And you'll see that it immediately crashes for us. And that makes sense. What happened is we were trying to establish a watch on a custom resource type that doesn't exist. So we'll deploy that first. We've created our custom resources. We're running this locally and we can see everything starts up. Again, that would be part of the flow if we were installing this as an image. We would deploy the custom resources, we deploy our service account, and then we would start up our operator. In the middle here, I'm going to establish a watch just on all of the different Kubernetes resources so we can see them get created once we create our custom resource. So we can follow all of the different child pieces. And then I'm going to edit the example custom resource that was generated for us under deploy and CRDs. And we're just going to set some sensible defaults here. Hello, J4K. And this is going to get us past the validation that the custom resource definition is going to require. That it's going to require we specify the title and the size. So I created the custom resource and you saw everything snap into action. It actually went extremely quick because this is, I already have all of these images pre-downloaded. So what it did was made sure MySQL was running. And if I scroll up, we can see that check where it said MySQL isn't running. We're going to wait for 5 seconds and then trigger another reconcile. After the second one, it was already running, so we were pretty good to go. Once that happened, we started up our front end and our back end. I get our Minikube IP, bring a window over here. And we can see the application is running. Oops. Then every time I hit refresh, it is sending that request over to the REST API saying, hey, I have a new visitor. That's writing it out to the database. And then this page is constantly polling the REST API. So again, very whirlwind tour. Take a look through the code on your own. It's going to be a little bit easier to process now that you've seen these start to finish. But the point being, we created our custom resource definition. We implemented the reconcile loop. And then we started everything up. And that's effectively all it boiled down to. Once we created our custom resource, the operator received that request through its watches, and it took the action to create all of the necessary resources. So to wrap things up, I have a couple of resources, some contact information. I've likely been pasting all of this into chat as we've been going, but on the Git repo, you're going to find all of the code that I cheated and copied in. We can find the actually fully built operator as well up there, so you can see all of the pieces and trace through them. You can reach me on Twitter at JDob or just follow me on GitHub. And speaking of GitHub, that repository that I link at the top there, if you have any questions or you run into any problems, by all means, feel free to file an issue there and contact me that way. Otherwise, feel free to reach out to me on Twitter if you run into any questions. Thank you. I know this was a ton of information dumped on you in a short amount of time, but I hope you enjoyed it and enjoy the rest of the conference.